All right, folks, back here with another video. What we might think of as the second half to that study of the derivative for our trigonometric functions, folks. We had looked at in another video the derivative rules for our two fundamental trigonometric functions, that being the sine and the cosine functions. I want to come back in this video and spend a little time looking at the other four cases, looking at the derivatives for the tangent, cotangent, secant, and cosecant functions. All right, and take note on those values. Now, if I go ahead and bring the notes into view, here's the notes, right? Where I already have the sine and cosine established, right? We understand the derivative with respect to x for the sine of x is the cosine. And we understand the derivative with respect to x for the cosine is the opposite sine of x. All right? Where for the other four trig functions, we bring those up into view. What we see for the tangent is that the derivative for the tangent of x is equivalent to the secant squared, where the derivative of the cotangent is equal to the opposite of the cosecant squared. And the derivative of the secant is equal to the secant times the tangent of x. And the derivative of the cosecant is equal to the opposite of the cosecant times the cotangent of x. And what we might see with each of these pairs of cofunctions and their derivatives, right? Sine and cosine are cofunctions. Tangent and cotangent are cofunctions, right? Secant and cosecant are cofunctions. What we might see in their pairs are patterns in their results. Right? We see the cosine produces the opposite sine in pattern. Whereas the secant squared of x, careful there, the sine's derivative is cosine of x in pattern, whereas the cosine's derivative is the opposite sine. We see a similar pattern in terms of sine with the derivatives for tangent and cotangent, and similar behavior in terms of cofunction. The derivative of tangent is secant squared of x, where the cotangent is the opposite of the cosecant squared of x. The tangent and cotangent's derivative involves the cofunction pairs, the secant and the cosecant, just like the sine and cosine derivatives involve those cofunction pairs, the cosine and the sine. Where also in the cotangent case, we are looking at the case for it being negative. And then for the secant cosecant cofunction pair, we see the following results that are also cofunction pairs. Right? The derivative of the secant being secant x tangent of x, and its derivative of its cofunction, the cosecant of x, being the opposite of the cofunctions for that derivative result. Right? The opposite of these functions, or the opposite of these functions, cofunctions, which are the cosecant of x and the cotangent of x. Right? We can note that pattern, first of all, in all six of the derivative results for our trigonometric functions. All right. Now, I want to go through a little bit of proof before we dive into an example here. The tangent and cotangent proofs are very similar, so I'm only going to work with one of them here for the sake of time. I'm going to work through the derivative for the tangent of x, and we're going to show its proof. And similarly, the derivative for the cosecant and secant are also very similar to each other. So I'm going to go ahead and work through the proof for just the secant of x. And the proof for the cosecant would be very similar in its process. And how we prove these is we move outside of our definition of the derivative, and we rely on a proof, right, that now just makes use of the quotient function. Right? For proving the tangent of x, proving that it's equal to the secant squared of x, we do rely on the idea that the tangent of x is just the ratio of sine to cosine. The tangent of x is just the sine of x divided by the cosine of x. And there we have the quotient of two functions. The quotient of the sine x with the cosine of x. Sine x being one of the functions, cosine of x being the other. Where we know they're individual derivatives. Derivative of sine is cosine, derivative of cosine is opposite sine. And if we arrange those derivative results, as well as f and g, into our quotient rule, from the quotient rule, we'd be able to say that the derivative of sine over cosine is the cosine of x times the derivative of sine x, right? It's our denominator times the derivative of the numerator for this first term, minus our numerator times the derivative of the denominator for our second term, which is what we see right here. And all of that is placed over the cosine squared of x. Where if we evaluate those derivatives, we know the sine of x's derivative is going to give us a cosine of x. And we know the cosine's derivative is going to give us an opposite sine of x. So if we bring those results into play, right, we will have this statement here, the cosine of x times the cosine of x minus the sine of x times the negative sine of x, where what we would notice is if we simplify that, it does simplify into the statement the cosine squared of x plus the sine squared of x, which we should identify as what? The fundamental identity of trigonometry. That Pythagorean identity of trigonometry, where the sine squared plus the cosine squared of an angle always equate to the value of 1. So that numerator, when we apply the quotient rule to the tangent of x in the form of sine over cosine, will simplify to simply the value of 1. And what we have here is 1 over the cosine squared of x, where the reciprocal of the cosine we understand is secant. So the reciprocal of the cosine squared is going to correspond to the secant squared of x. And we see that become the result of our derivative. And thus, for the tangent, the derivative with respect to the tangent of x from quotient rule is equal to the secant squared of x. And an analogous proof can be shown for the derivative with respect to the cotangent, because it is the derivative with respect to x. Let me go ahead and throw this in here. For what is the cosine of x divided by the sine of x? Right. So let me go ahead and highlight that. We can show an analogous proof for the derivative of the cotangent, where we just approach that looking at the derivative of the cosine over sine, again applying a very similar quotient rule as we had seen above. Right. I'll let you attempt that on your own, but with quotient rule, all you're applying is quotient rule to cosine over sine. If we look at the derivative for the secant of x equaling the secant tangent of x, we also use a little quotient rule. What we notice about secant of x, or note about secant of x, and we've said this in the above proof, is that 1 over the cosine of x is equivalent to the secant of x. The secant of x is the reciprocal of the cosine function. Where here, if we think of this as 1 over the cosine of x, we can consider this to be the case for a quotient of two functions, 1 in the numerator, cosine of x in the denominator. So it's going to be cosine of x times the derivative of 1, right, minus 1 times the derivative of cosine x, all over cosine of x squared. So again, from quotient rule, we can say something similar for 1 over cosine x. It is the cosine of x times the derivative with respect to x for 1 minus 1 times the derivative with respect to x for the cosine of x, all over again the cosine of x squared. Right? Now the derivative with respect to x for 1 is just 0 because that 1 is a constant. And we know the derivative of cosine is opposite sine. So multiplied by this negative 1 will turn into positive sine of x. So what we would have here is 0 plus the sine of x in the numerator over the cosine squared of x, which does simplify to the sine of x over cosine squared of x. Where we can take that statement there and break it apart into the product of the sine x over cosine x with 1 over the cosine x, where sine x over cosine x we again understand is the tangent of x, and 1 over cosine x again we understand is the secant of x. And again, thus by quotient rule, the derivative for the secant of x, right, is just the tangent of x secant of x. Right? And an analogous rule can be shown for the cosecant of x. Right? Since the cosecant of x is the derivative with respect to x for 1 over the sine of x. So we might as well highlight that in the notes here. But we can show a very similar proof, what I call it, what's known as an analogous proof. Very similar looking proof. All right. Now, we might look at an example, right, involving, here we have the tangent of x. And I say, consider finding dy dx for y equal to the tangent of x divided by x squared. Well, from quotient rule, right, we do have the quotient of two functions when we consider this derivative with respect to x. I should probably note dy dx is equal to the derivative with respect to x for the tangent of x over x squared, where we can say that takes on the form of this quotient, f over g. Where we should be able to identify what is f prime, and that's the derivative of tangent of x. We know that's secant squared x. G of x is the x squared found in the denominator minus f of x, which is going to be just the tangent of x times g prime of x, all divided by the quantity g of x squared. G of x being x squared again. Right? Letting f equal the tangent and g of x equal to x squared, right, implies that the derivative of y with respect to x for the tangent of x divided by x squared is equivalent to this setup for the quotient rule. It is x squared times the tangent of x minus the tangent of x times the derivative of x squared, all divided by x squared squared. Now the tangent of x gives us secant squared. The derivative of x squared is 2x. And x squared squared in the denominator is x to the 4th power. So if we simplify that, we might say that becomes this here. This first term becomes x squared secant squared x minus the second term, which is going to be 2x tangent of x. And all of that is going to be over the value of x to the 4th power. Now, one thing we will note that occasionally we're going to be interested in doing is understanding these results in the terms of sine and cosine. So one of the things we might consider doing here is, this is our result. This trig function is, or this result involving the trig functions is not a nice looking result. And we could present it differently if we want to just incorporate the two fundamental sine and cosine functions by rewriting secant squared and tangent as 1 over cosine squared and sine of cosine x. If we did that, we get a little closer to having a common denominator of x cubed cosine squared x in those two pairs. And we could convert over to a statement that looks like this in terms of sine and cosine. Right? But the truth be told, any one of these three statements is actually correct. We're at the point where there's really no one defined simple form. What we're often asked to do, however, is to convert things over into simple cases involving sine and cosine, which is what we see here in this result. We have turned this case involving secant and tangent into a statement involving the fundamental functions involving sine and cosine seen here. And thus, in its most fundamental form, we might say the derivative with respect to x for the tangent of x over x squared is x minus 2 sine x cosine x, all divided by x cubed cosine squared of x. And we could use this as our derivative result. If we were to push that result to being in its simplest form involving the fundamental trig functions sine and cosine. All right. I think that's the end of this notes. It is. There's, I think, all just blanks below there. All right. But again, here what we've just seen a presentation of with an example here at the end, right, are the derivative results for our four trig functions, that remain, the tangent, the cotangent, the secant, and the cosecant, where we were able to work through those proofs, prove those rules, right, using quotient rule and our knowledge of the cosine and or the sine's derivative value. And we set this up for the case of the tangent using quotient rule, and we set this up for the case of the secant using quotient rule to prove these two results. The results for the cotangent and the cosecant, however, will be very similar in their process. All right? But yeah, this is a pretty short video there, folks, because, right, our proofs there were probably a little simpler than what we're used to, relying simply on the quotient rule and our results for the sine and cosine. Right? And as we see for the results here, we're just looking at the results for 6 very specific functions. The sine x, the cosine x, the tangent of x, the cotangent of x, the secant, and the cosecant are 6 trig function derivatives. We've kind of moved away from advanced rules that require just generic functions f and or g, right? And we're back to looking at some very specific functional forms, right? So our results are a little quicker in that regard. All right. But with that said, I will end the video there. And what I am planning to come back to, I think, is implicit differentiation. I do think we need to look at some implicit methods. What do I mean by all that? And I will set that up. Reason being is our last 2 situations that we want to study for function derivatives of function types, logarithmics and exponentials, and the inverse of these, the inverse trig functions, are going to require some implicit derivative techniques. And you might be scratching your head going, well, what's an implicit derivative technique? And I'll say it's not what we're looking at right now with these. These are explicit derivatives. All right? These are explicit derivatives. Now, we could change them quickly and make them implicit, but I'll show you that in the next video. All right? I realize I'm highlighting something you can't even see. So we'll be back with this in implicit differentiation, folks, and we'll open it and discuss it all there. So I'll see you in the next one. And I'll end this here.